Okay, new section. Section 10.3, which is called Convergence of Series with Positive Terms. Kind of a long handle for this section. Okay, so I'm going to start off with a fact. Okay, if my series has positive terms, so in other words, all of the terms an are strictly bigger than 0. Okay, I don't have any negative terms. Then, if my partial sums are bounded above, then this sum converges. Okay, so finally we have a test for convergence. And if not, then the sum diverges. So there's really nothing to prove here because the sum is defined to be the limit of the partial sums. So it converges if and only if the sums converge. And you have to be very careful. This only applies for a positive sum, okay? So careful. Look at this sum, -1 to the n. This diverges, even though -1 to the n is bounded. And the reason that fails is just because this sum here does not have only positive terms. So this test does not even apply to this sum. Okay? Okay, next we're going to have maybe the most useful way to tell if a sum converges or diverges. It's called the integral test. So suppose that my sequence is defined by a function. Okay, so the integral test only applies if I have a lot of conditions. It has to be positive, decreasing, and continuous. Okay, and if it does, here's the test. If the integral from 1 to infinity of f of x dx converges, so does the sum from n is 1 to infinity of an. And if the integral diverges, so does the sum. Okay, this is a much more useful test than the test for divergence because it tells when the sum converges or diverges. So let's do an example. Let's try to decide if this sum okay, so if you write out the first few terms of this sum, this is 1 plus a half plus a third plus a fourth. Okay, the terms are definitely getting smaller. So it looks like it might converge, but we're just not sure. So the solution let's apply the integral test. Okay, f of x equals 1 over x. Okay, looks like this. Remember, I'm starting it at x is greater than 1, so I don't have to worry about this asymptote. Okay, so certainly this is positive, decreasing, and continuous. So I can apply the integral test. You can tell it's decreasing because it's going down, but you could also take the derivative and check that it's negative. So, rather than computing the sum, I'll just compute the integral. So let's look at the integral of 1 over x dx. This is an improper integral, so this is going to be the limit as t goes to infinity of the natural log of the absolute value of t, which we know is infinity. In other words, it diverges. So that tells me that the sum also diverges by the integral test. Here's another example. Here's a much more complicated sum. Okay, so to answer this, you just need to look at the function f of x is equal to x over x squared plus 1 squared. So this is certainly positive, and it's continuous. But is it decreasing? So to answer whether it's decreasing, you would just take the derivative. To take the derivative, you need to use the quotient rule. Okay, so when you do the quotient rule, you have this guy times the derivative of the top, so times 1, minus the top times the derivative of the bottom, which is going to be 2 x squared plus 1 times the derivative of the inside, which is 2x, all divided by the square of the bottom, which is x squared plus 1 squared. Or, sorry, to the fourth. Okay, when you simplify that, what you end up getting is 1 minus 3x squared divided by x squared plus 1 to the fourth. So this is less than 0 when x is bigger than 1, because you're subtracting this term. So this is decreasing because the derivative is negative. Okay. So now all I need to do is calculate the integral of this term. And I don't even need to calculate it, I just need to determine whether this integral converges. And this is a straightforward u substitution. So I will let u be x squared plus 1, so that du is 2x dx. So this turns into the integral from 2 up to t squared plus 1, and I'll take a limit as t goes to infinity of du over u squared. So the 1/2 comes from this 2 when you're replacing all the x's by u's. So this guy converges. This converges by the p-test. P-test for improper integrals tells you that if the exponent here is bigger than 1, then it converges. So if it converges, then the sum converges. So the answer is yes. Again, by the integral test.